I'm going to talk a little bit about search, and let's first ask a question to you guys. How good are you at finding your stuff? So raise hands if you lose your car keys once a week or once a month. Well, a couple of hands are going up. And if you lose your stuff, is it just like in my household? I mean, if you misplace your things and you cannot find them anymore, you raise a bit of a tantrum. It's never your fault. It's always your wife or your kids that replace stuff like that. Yeah, well, you're not the only one. And actually, the human brain is not really triggered for finding stuff. There's actually some pretty good research on that, and that says, well, the human brain is not good at finding stuff. What we typically do is we start searching in the places where we already know that we're not going to find our car keys. The best tip that you can take home from actual research is, well, start looking into the most untidy places, because that's probably the location where you put your car keys. And that's also a takeaway if you have, well, less untidy places in your house. If your house is really clean, then it's way easier to find your things. Or, like me, use technology. I mean, I'm addicted to AirTags for my keys. I don't have to bother my family anymore about lost car keys. I now use an app and I can find the keys again. So use technology. That's another tip that you can use. And if you want to keep your house clean, there's a simple rule as well. If you leave a room, if you see something that doesn't belong there, take it along with you and place it in the location where it's supposed to be. Then your house is kept clean. The picture you see is actually the picture of the the untidiest teenager room in the world. That there was an actual competition for that one. This belongs to a teenager in Scotland. Full disclosure, I think my kids' rooms are probably even worse, but I didn't get her permission to post a picture, so I'm using this one here. So a couple of practical examples on keeping your house clean for the physical things, but what if we want to do that with data? Well, I've been acting in finding the proverbial car keys for my customers for over 20 years now. That is by building data platforms, digital twins, and things like that. Mainly in the energy industry, where we're dealing with loads of data. That is up to exabytes of data that we have to deal with, and in that heap of data, we have to find our things. A modern development in there is OSDU, and I'm going to talk a little bit about OSDU and search in that context as well, and a focal point for OSDU for CGI as well. So if you want to apply those best practices for finding stuff in your data, well, data management, how to keep your house tidy, well, you simply start with process and people, right? I mean, you make sure that you have good workflow definitions here in your organization, so you know what kind of data is necessary for all the workflow steps that you're taking. You make sure that you have your technical data managers in place, business analysts, domain experts, data engineers. So if you have that small army of people working for you, that's a good first step to organize your data. Then you come up with your organizational principles for your data. So what is your master data? What does it look like? What kind of types are in there? How do I tag my data? How do I categorize my data? And what kind of retention policies do we keep to my data? I mean, I'm dealing with companies that have data that is, well, up to 70 years old. So do you really want to keep data for 70 years? What are entitlements and obligations for my data? So who is allowed to access that data, and who is supposed to work with that data and make sure that it has a high quality assurance on there as well? And of course, start applying technologies like RPA, to automatically scan your documents and start categorizing them. Apply search engines, and we're going to come into search, of course, in this presentation. Observation systems, so as soon as you see data appearing that triggers processes like QA control on your data, and make sure that you have good data engineering and data analytics pipelines in place to do useful things with your data. So all the necessary things that typical companies have in their digitization journeys. But there's a couple of practical realities. I already mentioned, I'm dealing with companies that have a history of sometimes 100 years, 110 years. My oldest company is 120 years old, and they've been collecting data since the late 60s. Back then it was all on punch cards and tapes and things like that, a little bit static. But a workflow that was defined in the 1960s is not the same as a workflow that is now defined in the 2020s. That also means that over history you have a lot of variety as well. I mean, the value chain becomes longer or shorter. I mean, the nature of your company is changing. If I'm working with an oil company, now they're moving into the renewable energy as well, where they want to have full control of the full power cycle, not just what is getting oil out of the ground or producing hydrogen based with wind energy or stuff like that, but also making sure that you are buying the electricity from them as well. Data velocity is changing as well. I mean, IoT is of course a new development, but we see a lot of fiber optic sensing in there as well. So if you use fiber optics and you have a fiber optic line where every 1 meter in there is an actual sensor. If you do that in a well that is 4 kilometers long or something like that, or you do that on a wind turbine that is 300 meters long, then yeah, is it measuring everything in a sub-second level with many sensors. So you're producing up to gigabytes of data per second in that sense. And with all our best efforts, we always know that data is going to end up in silos anyway, because we start doing something new with data. We purchase an application or we create a new application for it. It has its own data store in there. And over time, data has ended up in many silos. And silos can be as simple as, well, it is a file system and nobody knows what the file format is, only that specific application, or it is a very complex database with a database structure that nobody understands except for the applications that you're working with. In the energy industry, we started out with the OSDU effort. OSDU is an effort that is managed by the Open Group, and I think most people know the Open Group from TOGAF as well, but they're doing a lot of things with open architectures and open data standards as well. OSDU is one of those open architectures and open data standards as well. It is a forum that consists of over 200 active members. That is not just the oil and gas industry, but renewable energy in there as well. All the cloud providers are members. A lot of integrators like my company are members as well. Universities are putting their effort in there as well. The principle is that everything is cloud native and open. So there's a couple of reference architectures available with the cloud vendors that are all based on open source. The data standards are all open as well. And if you want to read out what the architecture looks like, you can simply log into their site and look at the architecture documents and things like that. So everything is open and transparent. And it is a platform that can scale, and I mean scale a lot, as in our smallest deployments are a few petabytes large. The largest deployment that we have with the customer is 2.5 exabytes of data that we're managing. So yeah, we do a lot with data. So that's why search is important as well. So the benefits are, with that platform, we make sure that data is available at your fingertips, so not anymore in all those disparate data silos that are out there. It's one location where you can get your data. Like I said, it is backed by the industry, and the industry makes sure that everything remains in an open standard. But if you want to implement it, well, it takes a lot of effort to implement it. So that is one of the reasons why my company has created CGI Pivot. That is a platform as a service version of OSDU. So we have created all kinds of smart logic to make sure that deployment is as easy as possible. And with a couple of clicks, you can deploy OSDU and you can scale it up into whatever you like, or you can scale it down, again, if you're not using certain data aspects anymore. One of the components in there is Atlas that we're using. So first go a little bit into the functional architecture. So you have your big, nice, shiny platform. Of course, you have all kinds of existing data sources. We're building more and more connectors to make sure that the data from those data sources can end up in the system. So we make sure that governance is being copied and distributed over OSDU. We make sure that there's good ingestion pipelines that can pick up the data and do things with it. But the important bit that we're going to focus on is the indexing bit. Because yes, the data is in your platform, but then it needs to become discoverable. So what does it look like? So we have a couple of data ingestion pipelines that could be real-time. In most cases, that is based on Kafka implementations, or more batch-oriented. That's done with Airflow DAGs, where we process the data and push it into the system. And once we push it into the system, the raw data is being stored in a data lake. That could be S3 or Azure Blob. But we keep the metadata in our record store, and that is based on MongoDB Atlas in our platform. One of the prerequisites for data in OSDU is that if you provide data to OSDU, if you cannot provide metadata, it's not welcome in the system, because if you simply push a file in and nobody knows what it is about, then it's kind of useless as well. So one of the rules is metadata needs to be supplied. Once metadata is supplied, we have indexing logic that is, scraping all that data, and it's preparing it for Elasticsearch. Elasticsearch is the de facto implementation for OSDU. So if you look at the reference implementations, you see an Elastic deployment in there as well. Well, that's where we have a little bit of a car crash, because all the data that we're using contains a lot of nested and unstructured arrays. And if there's something that Elastic doesn't like, is pushing what is unstructured data into an index. So that's what the indexing logic is about. It is actually chopping up that data into smaller partitions and pushing that into separate indexes to make Elastic perform in that sense. Once everything is in Elastic, from an indexing perspective, we can query it with Lucene. That is a little bit troublesome as well, because our domain is very expanded, or at least very extensive. So if we look at what relationships look like, I mean, this is a very small snapshot of just a couple of wells and fields that are associated with each other. We have graphs in our system that cover over 1 trillion nodes. So if you don't know what you're looking for, I mean, Lucene is good, fine, and dandy, but I'm going to come back on that one as well. You have to be a little bit targeted in what you're doing. Elastic was a bit of a problem for us. Like I said, we had to have those custom indexing logic things. I mean, we copied that from the open source reference implementations, but we do see that Elastic is not really, cost efficient when we deploy it. So what is it that we try to do to make it perform a little bit better and make it less of a memory hog? And in that sense, we started taking all the data types and moving it into separate indexes. But that's where we have a bit of a problem with cross-index searching. And if we have a new version of a data type, we pretty much automatically end up with yet another index in the system. So we have version 1.0 of a wind turbine, and then we have version 1.1 of a wind turbine, two separate indexes. But we want to simply search for one wind turbine. So how do we tell the system what index to look over? Yeah, like I said, we had to avoid everything with nested arrays. I mean, even if we push it into separate indexes, the nested arrays is still a problem. And since we have a platform as a service offering, it is also based on multi-tenancy. So we had to, increase the license versions of Elastic as well, so we could support more security. So we wanted to make sure that if you do a search for company A, that you don't end up with search results that come from company B or something like that. And we had to change the default search API, so we had to translate the data into the correct indexes and things like that. Well, since we were moving everything into separate indexes anyway, one of my developers said, well, since we're using Atlas anyway and search has been introduced, why don't we use search on Atlas instead of in Elastic? Let's go into that and what it means if we do that. Let's first give a quick example of a typical search query that a user would be asking. And the user is not going to enter something like Lucene. The user is going to simply ask the system, well, give me all the gamma ray logs, or give me all the gamma ray and the nutrient density logs. And I want them to be in an area where the 16/4 wells are. And it needs to be in the Brent Formation. I'm using a lot of, oil and gas jargon in here. I will come back on that one a little bit later, but it does show you that you need to have intelligence to start searching for the correct data. So from a technical perspective, we simplified everything with Atlas. What we simply did was, well, we are pushing all of our data into separate collections anyway. Even if we have multiple versions of a wind turbine or a well bore, things like that, we can push that into the same collection. We do, have distinct collections per data type, so it's not like a well and a wind turbine are in the same collection. We simply switched on the indexing per collection. In most cases, we see that the default settings are perfectly fine, no matter how much data we're pushing in there. And we could remove the indexing service in that sense. For some reason, Atlas doesn't care if we push unstructured subarrays in there. Atlas is perfectly fine with it, and we see that it is working in most cases out of the box. We do keep a regular check on, well, how is everything performing? It's something that we do manually at the moment. Everything is still performing quite well, but we're planning on implementing all kinds of observability in that sense as well. That's still immature at the moment, but there's still a little bit of remaining complexity. Like I said, I mean, the data is now going to be in different indexes because it is in those different collections. And if I want to do a search, well, I do have to do a search that is going to cross all those indexes. So I was pleasantly surprised when it was announced this morning that we can do, or we can soon do, cross-index searching. So I'm kind of curious, well, how is that going to play out? Because we have a lot of indexes in that sense. I don't want to do cross-index searching over all of my indexes in that sense. So there's a couple of challenges, I think, ahead in there as well. If we focus a little bit on that indexing bit, like I said, what we did in Elastic, we were pushing everything into a single index. That made Elastic slow at that moment, but from a search perspective, everything becomes a little bit simpler as well. Because if we start searching, we know that we can, access a single index, and we simply have to provide a good path hint to get to the data that we're interested in. If we do that in Atlas, we have the index per collection, and in our case, we were enhancing our search APIs to provide an extra parameter to indicate, well, now you have to search for this bit of data. And once we have found that data from a specific collection, we still have to combine it. So this is, I think, the main difference. I mean, in Elastic, we could do it with a simple path, and in Atlas, we have to extend our search API. So if we go back to that original query that we had, this is a query that is actually distributed over, in this case, just four indexes and 4 collections. The gamma ray and the neutron density, those are what we call well logs. I mean, oil and gas companies, if they drill a hole in the ground, they put all kinds of measuring equipment in there. What we're measuring, for example, is gamma ray radiation, neutron radiation as well, and then we know a little bit more about what the subsurface looks like. It is something that we're utilizing a lot in renewable energy with geothermal as well, and with the carbon capturing that we do as well. So there's a lot of subsurface knowledge, not just for the old oil and gas, but the renewable energy as well. Next to that, we are searching for wells. So that's the extra collection that we have to look on, and we have to interpret this query as something that we have to know that it's also location based. So we have to start looking for the blocks in which those 16/4 wells are located. And we have to know something about, well, Brent formation actually means that you're searching for a layer under the ground that is called Brent. It could be Jurassic or all kinds of things. There's many layers under the ground in that sense. So that does mean that you need to have a lot of domain knowledge if you want to interpret a query like this. Our system is quite flexible. OSDU is quite flexible. You can enhance it with new data types as well. So it's not like if you introduce a new data type that you know in advance everything that a customer could potentially ask for your system. So you need to have some kind of smartness that knows, well, if a user is entering a query like this, probably has to do with well logs. It probably has to do with formations under the ground. And if you're doing, or if you are correlating formations under the ground with well logs, there's probably a depth component in there as well. You need to translate that question into all those specific domain-specific items to search for the correct data. And we have to do that across those different collections. I mean, there's a little bit of data coming up from one collection and data coming up from another collection, and then we have to start cross-referencing to find out, well, is this really in the context that we're looking for? And to make that work, we're actually developing new, natural language processing logic to determine what is being meant with a query like that, so that we can kind of predict what indexes we have to search for, what kind of indexes we have to query in, and we can also create weight factors to come up with better results in that sense as well. And we're finding out that Lucene is excellent for finding data without having to construct all kinds of difficult aggregate pipelines. But we're also finding out that it's best fit for exploratory search. So the type of search results that we now come up with is very Google-like. I mean, you're typing something, and our best effort or our best guess on the data that you're looking for is then presented on the top, and it's lower ranking than it ends up in the bottom. So we do leave a little bit to the customer on saying, well, this is the search results that you're being returned with. Now you pick and choose what you actually want to have in there. First we thought, well, that's not exactly a good idea to do that, because customers want to have exact results, but we're finding out that customers actually like those fuzzy results, because it forces them to think about, well, there's another venue into the data as well. So we have simplified a lot with Atlas. The architecture has become simpler. We could remove that indexing logic. I mean, that was taking up a lot of compute resources, and we had to pay a lot for that. The Elastic licenses could become a lot cheaper as well. I mean, we're saving up to 6 figures per customer per month in that sense. And Atlas is scaling without there's a memory pressure in that sense as well. So that's something we really like as well. Elastic is a great product, but before your data is indexed, well, it is a compute-intensive and memory-intensive application, or platform to use. So have we got rid of Elastic completely? No. Elastic still shines in a couple of areas. So we now utilize it much more in our operationally oriented data. So we're not storing our log data or our other observability data in Atlas. That's something that we're storing simply in Elastic. Why? Because most of our open source observability tools like Elastic as a backing store. So, I mean, if I connect something like Jaeger or connect Prometheus to Elastic, I mean, it's very straightforward. It simply works. If I connect Grafana to it simply works as well. So that makes our life easy in that sense. So we use it as a search store for our observability data, and GeoJSON. Yes, there is GeoJSON or geographical information, support in Atlas. But if we do want to display it on a map, it is easier to do that in the ELK stack. And if we want to do geographic search, it's a little bit better as well. We'll go into a little bit more detail on that one as well. And we support depth in GeoJSON as well. Depth is an optional, or depth or height is an optional value in GeoJSON. It is something that is not supported in Atlas, but it is supported in Elastic. And if we want to display it on a map, I mean, if we connect a Kibana to an index, and I say, well, my Kibana dashboard is now a map, it automatically picks up the GeoJSON data, and whether it's a shape or a dot or whatever, it's simply being displayed on the map as well. And what we really like is the pluggability for our CRS services. So CRS stands for Coordinate Reference Systems. So anywhere where you're in the world, you're using specific coordinate reference system. So in my home country in the North Sea, we're using a range called the ED50 range. Here in Gulf of Mexico, I think everything is in the ED60 range. Why is it that we're doing that? Because the localized data is much better projected on a local map with the CRS that we're using at that moment. But if we want to display it on a central map, then we want to translate everything into WSD84, like Google Maps is doing as well. And the pluggability aspect in Elastic is something that we like a lot better than what we can do in Atlas. So conclusions. Well, saying goodbye is actually quite hard. I mean, yes, there's a lot of promise in using Atlas, but if you want to replace Elastic completely by Atlas, it's not that straightforward. I mean, Elastic is still shining in the GeoJSON area. Like I said, architecture has become a lot simpler, so we could get rid of those indexing services and a lot of license costs in that sense. But Lucene is quite hard. I mean, yes, we can do search on all those indexes, but if you don't know what you're searching for, I mean, you can type in something and you're overwhelmed with the results. So we do have to guide the system a little bit in what is coming out of the system. Like I said, we were pleasantly surprised with the announcement this morning about cross-index searching. So let's see what is going to come out of that one. Still, consider implementing natural language processing as a first buffer into the construction of your Lucene queries. So a user is not being bothered with Lucene at all. Our NLP engine is creating the Lucene in that sense and also picking the right indexes to work on. And document databases are not the only thing out there. If we want to do calculations on weight factors, for example, for Lucene, we heavily rely on graph databases as well. So consider stuff like Cypher and Gremlin as graph languages or graph analytics to find out, well, what is the correct type of clustering of data that I'm using. If I can connect that to the search query that I'm executing, sorry, then I know what kind of weight factors I can produce and select the correct indexes in that sense. And we use that for page ranking and clustering as well. We are working on an open source version of all the search stuff that we're doing. If you follow the QR code, you now end up on an empty page. Open source is kind of new for my organization as well, so I'm still in a legal struggle to open up a couple of the data items in that sense, but it is going to consist of a quite extensive data set supporting all those queries. We have some Python code that can be used to generate your indexes on Atlas. Sample Lucene. The Lucene bits that we're going to publish is actually the tricky bit because the Lucenes that we now have a lot of customer references in there as well. So we need to weed them out. Python code for the Lucene generation and cross-index searching, and some GeoJSON fun, of course, as well. Although limited to the kind of 2D space as Atlas is supporting it, and not the 3D space as Elastic is supporting it. That was my very quick talk, and I open the floor to questions and answers. Yeah. No, it's more a practical consideration to use Elastic, because the connectors that we have with Prometheus and Jaeger, I mean, Elastic is a default backing for those. So, and since we already have Elastic, so let's simply push it in there. We simply didn't have time to say, well, let's create a new connector and push it into Atlas. We do have a lot of time series data in the OSDU platform as well, but that's what I think we're mainly using FluxDB in there, because Flux is supporting time, time zones, and that's a lacking feature in Atlas time series as well. So, any other questions? Well, if you come up with a later question, I mean, you don't have to use Lucene. I mean, you can simply find me somewhere on the floor here. Thanks for your attention.